All right, good morning. All right, so we have a subject today. We're going to talk about marrying OpenStack cloud with bare metal cloud. And so we'll get into what that is. But to start off with, let me just introduce myself and Pete Lumbus. So Pete is a technical marketing engineer at Cumulus, which means he knows where all the skeletons buried, and he's got firsthand experience. So we're going to bring some best practices in part of this discussion. Myself, my name's Dave Isles, and I'm a senior director with Mellanox Technologies. So I'm the hardware side of this, he's the software side of this, and together we're just going to talk about not vendor stuff, just more technology stuff. And there's should be ample time at the end to address any questions. So if you have anything and you don't think you'll remember it, write it down. But we will have time at the end to talk about that. With that, I'm going to go ahead and get started, and we'll hand off halfway through.
Yeah.
All right. So let's start off with just defining some terms. We talk about multi-tenancy, and we'll tell you multi-tenancy is different than single tenancy, right? A single tenant network is one tenant. It's a good example is SaaS customers, software as a service. These are guys that have one tenant, it's themselves, and that's relatively easy. The job of the network is to get packets from one side to the other side of the network. I can't stress how much easier that is than the multi-tenant network, right? A multi-tenant network, now you're taking a network and you're carving it up. You're saying, I'm going to take this same infrastructure and pretend like it is 2 instances, 20 instances, 1,000 instances, because I have different tenants that may be competitors with each other. They may be nefarious, so I have to protect them from each other. I have to guarantee service to them, and I need to carve up that network. In fact, I may even have different security policies for one set of network clients, one set of tenants, and another set of tenants. So multi-tenancy tends to be harder because of the security implications. So let's get into how you get multi-tenant networks. So the easy way, the old school way, is just VLANs. And if you have a very, very small network, you might say, hey, I'll just use VLANs because it comes with the technology. And I was doing Ethernet back in the 90s when they introduced 802.1q, and it was great, 4,000 VLANs. That seemed pretty amazing. And the nice thing is that isolated. If I want to go from one VLAN to another, that meant I had to go through a router. Right, so that's the good and the bad of it. And the other nice thing is OpenStack has pretty good support for VLANs. I have an ML2 plugin. It can go ahead and configure VLANs on every single server, on every single top of rack switch, and on every single switch between those two servers. So that's good, but it's also bad because it means that OpenStack is kind of a controller that has to not only poke every server, but has to poke everything in between those servers. And that means those VLANs have to be everywhere. And I'm just going to start by saying, so while it sounds easy, VLANs are not your friend. Right? They do solve the multi-tenancy problem, but you end up with a bunch of cons. And a big part of it is scale out. So a lot of times, because VLANs can't move across layer 3 boundaries, a VLAN can get trapped in a modern design. The other alternative is to say, well, no, I'll use big scale up switches, and I will just stretch VLANs everywhere. Well, the problem is that the size of your fault domain is the size of your broadcast domain. If I have one malfunctioning NIC that starts hammering everything, it's allowed to hammer everything in that broadcast domain, which means your entire data center could be your fault domain. And there's other, of course, problems with the VLANs in terms of the scale, how many you can get. But the big problem is it doesn't fit with modern leaf and spine architectures. It doesn't scale out very well. And so with that, I'm going to pass it on to Pete to talk about how VXLAN kind of addresses some of these things and how we go about doing it.
Thanks, Dave. So really what the futures move towards, away from that traditional VLAN-based model to VXLANs, is we can provide that same layer 2 extension for things that require clustering or some HA functionality, as well as the isolation that VLANs give us. But instead of having that 802.1q VLAN tag, it's now called a VXLAN ID or VNI. But what's really cool about it is it operates over a layer 3 network. So where VLANs require end-to-end layer 2, end-to-end VLANs, kind of everything looks the same across the board, and I only get that one layer 2 path, or maybe I can do bonding and get 2. VXLANs allow me to actually run over a routed network and have 3, 4, 6, 16, 32 different paths I can use. So I get a much more robust network that I can build on top of. Much smaller blast radius. Instead of my blast radius of failure being the data center, it now becomes a link or a box. Extremely high bandwidth is possible with this scale-out networking. So again, I can use every one of those uplinks out of my rack. Instead of just 2, I can have 4, 6, or 16 out of that rack and get all of that bandwidth. And if we start thinking about storage or NVMe, which we'll talk about in a little bit, I'm really pushing hard on bandwidth, and I don't want to just have bigger and bigger boxes. I want to scale that out. Because the other thing we have to think about is that if I lose one of those spines, those top-level switches, what's the impact of bandwidth? And in the VLAN model, I get these 2 giant chassis, and if I lose one of those giant chassis switches, I lose 50% of bandwidth. If I disassemble those chassis switches into 8 smaller switches, instead of losing 1/2, I lose 1/8. And the other thing that's really great about this is ML2 speaks VXLAN, but I can have a smaller ML2 footprint. So I can have OpenStack ML2 provision just the compute nodes as well as my top of rack nodes, but they never have to provision anything on my spines, on those core nodes. Because the VXLAN information only lives at those edges. The middle part is only responsible for transporting information from one side to the other. You start to look a little bit more like a traditional service provider cloud, where the service provider in the middle doesn't really care about what you're doing. It's just there to get data from one side to the other. So one of the options here is just looking at compute-based VXLAN. This is actually a great solution for extremely large-scale OpenStack deployments. So I'm going to run VXLAN not with the network itself, but from compute node to compute node. And so VXLAN is not on the switches, but directly out of the server. The way I can accomplish this is I can run BGP out of the server using open source software like free-range routing, and have the server advertise its endpoint into the network. So I don't have layer 2 anywhere. I don't have VLANs anywhere. It's an entirely layer 3 network. My server speaks BGP to the top of rack switch to say, hey, this is my VXLAN endpoint. And ML2 will then provision those VXLAN tunnels from compute node to compute node. So we're reducing that ML2 footprint all the way down to just compute. We have scale pretty much as large as you can build, and no VLANs, no shared blast radiuses anywhere. The other thing that's really great about this is that if we love the DevOps, everybody's one team, dream, but the reality is we still have compute and network. Most places still have some siloing, and this can help you with that siloing where, look, I'm a network person, that's my background. Get your dirty ML2 controller off of my switches. No, you can't run an agent. No, your stupid compute node can't touch my switch. And there's no way in hell I'm gonna let you push config to my box. This solves all those problems. You as an OpenStack manager, an infrastructure owner, can have ML2 drive that component. You can do BGP to your top of rack switch, and it acts like a demarc, just as that network engineer would provision something to a service provider handoff. So you apply rules, you apply filtering and policies, you don't necessarily apply trust. But you as that infrastructure owner totally control your fate from one side to the other. So that's super awesome. I love this solution, but I'm also a realist and know that it's not perfect. So the first thing is you're likely going to need VXLAN capable NICs. So to add that extra encapsulation, and we'll talk a little bit about what VXLAN and how it operates in a minute, to add that extra encapsulation requires some extra CPU cycles. Well, I don't want to take that CPU hit, so I'm going to end up looking at specialized NICs like the Mellanox X-series NICs to be able to do that offload on the NIC itself. that might not be an option for my infrastructure, or it might put the total cost of build too high. BGP to the server is scary. I think it's super cool. I've seen it deployed a bunch of times at pretty large scale, extremely successfully. But just the idea of running BGP to the server terrifies both compute and network people equally. It's like the one time everybody agrees is that this seems really scary. Network people, again, don't trust server folks, and server folks say, well, networking is stupid, why would I ever learn that? So you can go pound sand. And the reality is it's a complicated solution. This is a solution that scales extremely large environments. If I've got 10 racks of OpenStack, this is a ton of work for what, right? I'm never going to scale to a mega cloud. I'm going to scale to a dev pod. So why do I want to jump through all these hoops? And so it is a more complicated solution, but that's what you get the trade-off for a more scalable solution. And it's difficult for bare metal. So if you're looking at ironic deployments, this provisioning is challenging. There's a little bit of a chicken and the egg in which, how do I provision a server to do multi-tenancy that isn't provisioned yet? How do I do multi-tenancy out of a server where I'm expecting a hypervisor layer to exist to provide isolation? I don't have that anymore. It's not that it can't be solved, but it becomes a much more challenging problem to solve. So, VLANs are bad, right? You have that shared blast radius. You shouldn't do it. Really beyond one or two racks, don't do VLANs. You look at some of these other solutions. Look at VXLAN with compute and network-based, right? It's great, but it still requires ML2 on the network. One of the big challenges here is that when we look at the compute side, that ML2 state is ephemeral, right? That's cloud, that's beautiful, that's great. And so if that compute node reloads, it reboots, the server crashes or whatever, that's fine. I lose those VMs, I lose that network programming, I reprovision that wherever else. What if my switch crashes? Well, now I have a whole rack full of VMs with no network connectivity. That switch comes back up and it's lost all of its ML2 knowledge. So now what? So now I have a switch, it's got links, it's got routes, but I don't know anything about those tenant networks. I don't have a way to go back to ML2 and be like, hey, all that stuff that you've told me over the last 6 months of all the networks that I should have and shouldn't have, can you just tell those to me again? Right? We don't really have that ability. Some vendors have some kind of middleware solutions where they can replay ML2 information over time, but it's not universal. And again, the solution still requires VXLAN offload NICs. VXLAN compute only removes that ML2 on the network problem, but it's only good if you're OK with BGP on your servers. Right? Again, you have to be willing to do something a little different, be willing to think out of the box a little bit. And again, if you're looking at a really heavy bare metal deployment, this might not be the best solution for you. And so what do we need? Right? We need stability when we're building a cloud. Right? I can't have the loss of a switch bring down a rack of compute. I can't have the reload of an ML2 agent on a switch lose all the network connectivity, all the programming that exists for all of those underlying tenants. I need simplicity. I don't need to hire the Avengers to run my network. Right? I need to have, Pete from Deadpool run my network. I need flexibility, right? I need something that works for both that bare metal and those virtual services, right? I can't have something that only works in a virtual environment. I can't have something that only works for bare metal. I need scalability, maybe not, thousands or tens of thousands, but a few hundred tenants I think is totally reasonable for most environments. And I need affordability. Again, VXLAN capable NICs may not be an option for me. And so the answer is VLAN-based compute. But didn't I just violate the prime directive here? Didn't I just say not to do this? Well, I'll do VLAN-based compute and a VXLAN-based network. But it's not hierarchical port binding if you're familiar with this. So with HPB, ML2 is going to come in and it's going to poke VLANs and it's going to poke VXLANs and it's going to glue the two together dynamically for every provisioning. This is not that. This is only having ML2 provision VLANs. The network itself is totally pre-provisioned. So I'm going to build my VXLAN tunnels ahead of time, have those ready to go. I'm going to have my server-facing ports provisioned ahead of time and ready to go. And then I'm going to allow ML2 to come in and provision VLANs on my compute node only for the tenant that exists. So I have a configuration on my network device towards a compute node that says allow VLANs 1 to 100. And then as I spin up the tenant in VLAN 10, ML2 adds VLAN 10 to the compute node. And as I spin up VLAN 11, or I'm sorry, tenant 11, that gets added to the compute node. So the network is ready to receive everybody, but all that gets sent out of the compute node is what ML2 provisions. I don't need VXLAN offload for the network anymore, or the VXLAN offload on the NICs anymore. I allow the network to do that. And that actually makes it much, much easier for those bare metal deployments now, because I can allow the network switch to provide that VXLAN capability. And so this solution isolates that failure domain, isolates that blast radius, and easily can scale to hundreds of tenants, right? I can put 1 to 200 VLANs in a switch and not really worry about it. But the thing is that now my failure is only related, only isolated to that one top of rack switch. I'm not extending that layer 2 domain across my data center. I'm not going to bring down a TOR, all of my backbone spines, and the remote TORs from a server NIC problem. So the VXLANs get pre-configured between all the switches. So I have VXLANs across that network infrastructure. The compute-facing ports have VLAN trunks configured across them. And then ML2 only provisions at that compute layer. So every VLAN gets mapped to an identical VXLAN tunnel, or VNI. I don't need to do anything magical here. If you're familiar with VXLAN, you might know that it scales to 16 million on paper. And so I have this ability to do number reuse and VLAN reuse and things like that. You absolutely can do that, but that's not really what we're trying to do here. We're trying to solve for a few hundred tenants, not for 10,000 tenants. Right? We're trying to solve an L2 blast domain problem, not a hyperscaling problem. Because the hyperscaling problem, that solution is compute-based VXLAN with routing. This is a much more pragmatic solution for small and medium-sized environments. So VXLAN without a controller, what do we really need when we talk about VXLAN? Right? What is the information that's required? So I need the who. Who's the VXLAN endpoint? Who do I terminate this VXLAN tunnel on? I need a what. Where do those VXLAN tunnels exist? I need the where. What are the MAC addresses within VXLAN that I care about? And where do those live? So the first way to get this information is from a controller. OpenStack ML2 is the example. Something like OpenContrail, or now it's called Tungsten Fabric, or Open Daylight, are some of these examples of controllers. But I have this basically a database, and that database is going to push information out to the network about who owns what and what lives where. Option 2 is EVPN. So the switches will exchange data without a controller. So I have my network. They're all going to exchange this information without that controller. This is based on an extension to BGP. It's in most modern stacks, and it's fully multi-vendor. I know we at Cumulus have done interop testing both in our development as well as in customer environments with all of the major vendors out there. So it's fully standards-based, so I can have Arista on one side of my network and Cumulus on Mellanox on the other, and I know that it'll work just fine. So to dive in a little bit more on EVPN, the switches themselves are going to build BGP relationships. And I'm going to use that to advertise MAC address information. So as I learn about server A and I learn about server B, I'm going to tell the network, hey, I know about this MAC address. If you're trying to reach it, you come to me. And we're going to do that through BGP messages. Historically, there was absolutely no message that was sent to tell anybody about where a MAC address lived. This was part of the problem in layer 2. So that MAC address gets exchanged via BGP. We tell everybody in the network where all of these MACs live and how to reach them. And then when I send data, I take that original packet on the inside from server A to server B, and I wrap it in a VXLAN packet. And that VXLAN packet goes from switch A to switch B. And so again, I'm acting a little bit like a service provider in that middle. So that device up top, again, what we would usually call a spine switch, doesn't need to know about all these MAC addresses. It's really focused on being an extremely high-speed device. I don't need a big, complicated chassis with a bunch of features there. I need some really, really high-speed transport there. And then I'll put that complexity down to the edges. And since we're using BGP, we don't have those same layer 2 shared failures. I'm not going to get looping. I'm not going to get one server NIC going out of control, bringing down my entire environment. So there has been some movement with OpenStack and Bagpipe to do something that looks somewhat similar to this. So Neutron, again, they call it Bagpipe. And it's really got two goals. One is doing VPNs between data centers. But the other one that's a little bit more specific to what we're talking about today is layer 3 down to that compute node. So to have the compute node do layer 3 out of it. So if you're familiar with Bagpipe, you've looked at it at all, it's going to sound a little bit familiar to what I'm talking about. I'm not talking about Bagpipe. You can do what Bagpipe is trying to accomplish today with free-range routing. Again, this is an open source routing suite. How many folks in here are familiar with Quagga or have run across Quagga before? How many of you actually use Quagga somewhere? OK, so a fair number. So Quagga was forked off recently into a project called free range routing. If you're using Quagga today and it solves a bunch of problems, but you probably also yell at it pretty frequently, take a look at free range routing. It's the Quagga fork that's updated and being driven pretty quickly. But I can combine free range routing, FRR, and Neutron and accomplish a lot of the same things that Bagpipe is trying to do. You know, Bagpipe would have the ability to speak to OpenStack. So this is the difference, is that FRR is not speaking directly to OpenStack, where Bagpipe would. So Bagpipe would allow some of those dynamic BGP peerings to happen, where FRR is falling short there. I think, you know, if this is an area you're interested in, I would love to connect you to some FRR folks. But today, we would still rely on Neutron to provision VXLANs and BGP acting independently. This is nearly identical to EVPN on the server. It's still kind of early days. We've seen some work with FRR doing EVPN to the server. But the reality is the upstream Linux kernel isn't there yet. The patches exist, but I don't think that they're carried by anybody. So we at Cumulus have written a lot of the patches to the Linux kernel to support EVPN on the host. We carry those patches, and we're working right now with some customers to try to do EVPN down to the server. But I'm not aware of anything in production today. And it's still early days for Bagpipe as well, right? This is still something kind of actively undergoing deployment, development. And whether or not it's production ready, I don't think I can give you an opinion on. But it's something that I would solicit others for.
Awesome. Thanks, Pete. So the other thing, so just to mention, this is moving forward. So Bagpipe and things like that. The next OpenStack Summit we'll have a similar topic, but we'll talk more about how you likely will have EVPN running on your servers, talking BGP, exchanging all that who, what, where information directly. And it's kind of exciting because then you'll have the switches talking directly to the servers in many cases, as opposed to right now it seems like we've come up with a great solution for, let's say you have 100 racks of servers. What we described today is going to scale very, very well. If you've got 10,000 racks of servers, well then the first proposal kind of makes more sense. Other next generation things that are happening in a data center near you. So there's some new workloads. One of the reasons why people want things like bare metal servers is because they want to do things like machine learning applications. They've got GPU accelerated servers that are being offered. And you still want to be able to run that over a VXLAN network. And so there are some considerations to say, hey, listen, as I'm carving up my network with VXLAN, I got to make sure that all of the congestion notification features that go with machine learning, all of the kind of lossless fabric type applications needs to work on that. And I bring this up in the same context as NVMe fabrics because, let's face it, NVMe is coming to a fabric near you as well. So this is a growing area of interest, and they have very similar needs. Both machine learning and NVMe fabrics kind of are built on RoCE, which is kind of using this RDMA technology. And RDMA is just basically saying, hey, one server wants to access memory in a neighboring server, and they don't want to have to interrupt the neighboring server's CPU to copy every single packet. They'd like to offload that to the NICs. And so having NICs that will offload VXLAN and offload maybe RoCE at the same time is interesting. But in the model we described, you don't have to do that, right? You've got the network doing your VXLAN and doing a lot of your RoCE stuff. So you need the network to do both. And so if you look at best practices or things to worry about, kind of gotchas. So we talk about here are the great things about EVPN. There's a couple gotchas that we see in some vendors out there. And one of the gotchas is we feel that you ought to look for a solution that doesn't charge licenses for BGP. BGP is the language of the internet. You shouldn't pay extra for your switch to do switching. The same thing's true for things like VXLAN. You shouldn't buy a switch that can't do VXLAN today. And to say, well, we're going to charge you an extra license to do that seems like gouging. Same thing with ZTP. You guys all do Pixie boot on your servers? Right? Do you pay a special license to Pixie boot your server? No. Why would you pay a special license to Pixie boot your network? And so we think that things like EVPN, VXLAN, BGP, these are all table stake features that come standard with a switch, right? If you don't do those things, are you really a switch? Other things. So we talk about VXLAN. There's VXLAN routing that should be done in hardware. You shouldn't have to do any special games where you take a loopback cable and route traffic out of a switch back into a switch. If you see that, maybe you ought to look at a different solution out there to avoid that. The other thing to look at is scale. So you start looking at switches and you're thinking about VXLAN, you're thinking about EVPN, start doing a little more homework on how many VTEPs each of these switches can support. So we didn't get into the details of how head-end replication works for EVPN, because that's probably not in the 101 class that we're doing in like 40 minutes. But you are asking the switch to do a lot of extra work, not just tunneling and doing BGP, but sometimes discovering things and flooding things. And so the amount of remote VTEPs a switch can support, many of them are very, very small. And as we go to the next generation where those neighboring VTEPs may not be another switch, it may not be 100 racks, but they may be a bunch of other servers. Right? As we talked about the servers, you may tunnel between a switch and a server in the next generation. Well, then the number of VTEPs that you can support in hardware becomes pretty important. And then lastly, as we talked about some of these next generation kind of workloads, machine learning, NVMe fabrics, you guys are looking at Ceph and you want to do RDMA on Ceph. You're trying to like kind of turbocharge your storage that way. You want to make sure that also works with your VXLAN. So make sure that as you're looking at, otherwise you end up with a completely other fabric for your storage or a completely other fabric for your GPU direct type applications. Because you want to be able to carve those things up with VXLAN just like you do your non-lossless traffic. That's the kind of the whole point of converged solutions. So with that, I think we ended with plenty of time for questions and answers on kind of what, how this works or best practices. If anybody has any questions about EVPN or VXLAN. If not, we are around. We can always, oh, hey, there's a question in the back. You'll have to speak way up. Oh, there's a mic.
Thank you. Excellent presentation by both gentlemen. It was really revealing a lot of things. One thing I would like to know is how do you compare, because you are NIC vendor as well as switch vendors, how do you compare this for use along with smart NIC, which is becoming very, attractive for some of the vendors?
Yeah, so we invest a lot in the first use case. So as Pete was mentioning, there's this infinite scale kind of use case that says if you are building, 100,000 node network, we'd push you towards that first solution where you're going to do a lot of offloading in the NIC. And if you don't have a NIC that does the offload, you end up, a lot of things that you may not realize this, but even in the non-offload environment, the NIC is actually doing checksum offload, it's doing TCP offload, it's doing a bunch of scatter gather, it's doing a bunch of offloads that are available in the cheapest NIC possible. And as soon as you go to VXLAN, if they don't do offload of VXLAN, most of those NICs also suddenly lose the ability to do all those checksum offloads that they've been doing forever. Because now you're handing them the packet already encrypted. So all of the stuff that even the cheapest NICs can do in a non-VXLAN environment now is kind of being done on a CPU core. And so, yeah, so I think that there is no one size fits all. I do think that we've come up with an innovative solution for, especially for bare metal hardware, where you can't have the bare metal server do the VXLAN offload. However, I think that if you were to go, like I said, next OpenStack Summit, we'll probably talk more about how someone might want to have a hybrid of the two. They will have some software VTEPs and some pure switch-based VTEPs, and everybody's going to be talking EVPN. I actually think that's probably the future.
So just to add to one more, on the EVPN side of it, what kind of support you do for E-line, E3, and ELAN and all those? Is it part of it?
So the E-line, E3 stuff are terms usually focused a little bit more on the service provider space with Metro Ethernet. It is very similar. I don't want to say we do those just because that's it's a slightly different problem space. But what EVPN does at its core is provide the ability to do L2 and L3 multi-point networks. So if you're familiar with VPLS, it replaces VPLS. The E-line functionality, where it's doing transparent point-to-point without any learning, there is some limited functionality from some vendors. Cumulus itself doesn't support it today, but it's something we've been asked about and we're looking at.
Okay, thank you very much.
Mm-hmm. Great questions. Oh, come on.
I guess regarding support for EVPN multi-site using the border gateway, are you guys looking at doing that, where it shields all the internal VTEPs and does route target rewrites and so forth into other sites in different pods?
Yeah, so to give some more context, with EVPN, right, when what we were describing, I kind of have to have global visibility of everybody within my domain, right? So everywhere that VLAN can exist or that L2 can exist, I have to know about everybody else that has that. So then when I think about data center replication, all of a sudden I've got like a whole ton of things that I got to keep in mind. So the idea is that I have an aggregation point at my data center edge that says, look, get it to the edge, it'll get it to the other data center, and then they'll have the details once I get it to the other data center. Yeah, we're thinking about it, we're working on it. I might be wrong here, but my understanding is that some of the standard stuff is a little in flux around there right now. And our motivation is usually to build it, 10 minutes after the standard, the ink dries.
Yeah, there's a draft out there, the Sharma draft, I think, or...
Yeah, so there's work in the space. I think we would like to see a little bit more of a consensus before we start investing cycles, but I can tell you we have more than one extremely large customer asking for these things.
Yeah.
So it will happen in the free-range routing project in the near future.
Yeah, but before they have that, I think we've got solutions that use Type 5 announcements that say, hey, we'll build a multi-pod kind of architecture, and then it'll be ready, again, with border gateways that say, and then later when the standard gets there, you can easily flip to the kind of the new method.
Okay, thanks.
Come on down.
We got two. So we got one on the right.
Well, he's first.
Your left.
Yes. Okay. Okay. Hi. So you described the CVPN where MAC address, where finding the MAC address is being done by the same mechanism as BGP. Can you remind the traditional way, like pre-EVPN, how they?
Yeah. So without EVPN, it's what's called flood and learn. So I'm going to receive a frame, and I'm going to send it out every single port because I don't know where it goes.
So same way as the traditional Ethernet.
So that's how it works traditionally, right? Is flood and learn. So with BGP,
VXLAN.
so with VXLAN, there is no flooding.
So how do they learn where the MAC address lives?
It doesn't work with silent hosts. So basically, when I hear an ARP request, I will respond locally and just say, yep, I know where that MAC is. I've just learned your MAC address because you sent me an ARP request. I immediately turn that MAC address into a BGP announcement and tell the whole network, hey, I just learned this MAC.
That's the eBGP.
That eBGP is the messaging for that. So basically BGP is listening to the MAC address table.
Okay.
And so when the MAC address table updates, BGP goes, I care about that information now, let me let everybody else know.
And what about VXLAN, but without EVPN?
So VXLAN is just a tunneling encapsulation mechanism.
Oh, I see. So it's not implemented there.
Yeah, so BGP is the control plane and VXLAN is the data plane. And so that comes back to that who, what, where problem. So VXLAN, I can build this tunnel and do this encapsulation. I mean, I could build the packet myself if I wanted to. The question is, who has the MAC address? Who do I need to send that packet to? I learned that piece of information from EVPN. If I don't have EVPN, then I need a controller like ML2 or OpenContrail to tell me.
Thank you.
Yep.
Hi. Are you also looking at including floating IP functionality in this setup? Or would you still
Sorry, can you repeat that?
So can you also do floating IPs in this setup, or would you still need layer 3 agents running somewhere?
For flow mapping?
Floating IPs.
Floating IPs, I'm sorry. So that would be the layer 3 agent functionality. So everything we've discussed here would be focused specifically on ML2 and L2 component, not on L3. So for L3 and floating IP, that you could do through free-range routing on x86 nodes. Cumulus today does not provide an L3 agent. We'll probably do something like that in the future. The big challenge is that almost everybody I've ever talked to that needs an L3 agent also needs NAT. And these switches don't support NAT.
Next gen.
Yeah.
Thanks.
Yep. Anything else? Yeah.
Regarding EVPN, you guys also support or VXLAN routing as well?
VXLAN routing, yes.
Tenant networks and stuff.
Yeah, so that's actually a really important point. So a lot of what we talked about today was just the layer 2 functionality. EVPN and VXLAN also has the ability to provide layer 3 isolation and layer 3 routing. So if you're familiar with MPLS L3 VPNs, EVPN and VXLAN can do basically the exact same thing. But one of the big gotchas is that you have to be aware of the switch hardware. And can that switch hardware do both VXLAN bridging, which is the L2, and VXLAN routing, which is L3? The Mellanox ASICs, the software supports them both. The Mellanox Spectrum ASIC supports them both. And then the other thing, just because we love things to be complicated, there are actually 2 modes of VXLAN routing. One is called symmetric, and the other is called asymmetric. And not all ASICs support all modes of VXLAN routing. And you care about that depending on interop.
Right, to elaborate on that, if you're talking to Cisco, you'll probably do symmetric, right? But there's other vendors that are asymmetric routing.
Yeah, and
Juniper
there's
is the-
there's scaling issues with the other, because then it means you'll have to have all VNIs on every switch if you want to do the integrated routing and bridging, which
Yep.
That's right.
you wouldn't want that.
Yeah.
Okay, and then Anycast Gateway features are
Anycast Gateway features there today. Yep. And so the Anycast Gateway feature basically says, if I think about a traditional model pre-OpenStack, I've got a firewall that's my gateway for a bunch of VLANs. And so I'm going to go over to the firewall and then come right back to go to the next server over in the rack. The Anycast Gateway feature says, well, instead of having that end-of-row functionality, I'll make every switch my local default gateway. So if I'm talking to 2 servers in different VLANs in the same rack, that traffic never leaves the rack. And so I'll always route locally. And so even if I move that VM, or I'm in the same L2 domain in a different rack, I still talk to that same local top-of-rack switch as my L3 gateway. That's Anycast Gateway functionality with VXLAN routing. All right. Well, Wes is coming over. We'll do this one over here.
Okay. Hi. I have a question about VXLAN pre-provisioning, because as I understand correctly, you have to pre-provision all VXLANs on the network to have all VLANs on the compute nodes. Okay, so what if one internet card will generate broadcast traffic because it's failed?
Yeah, so how would I handle broadcast when I have everything pre-provisioned is the question, right? So depending on the implementation, there's flood reduction or flood removal. So some implementations will not allow flooding at all. So you send a broadcast and I just throw it away. Other implementations, what they'll do is they'll replicate it to everybody. We have knobs to enable or disable either one. I would actually say in this environment, I would likely disable them. But you'll be shocked at how many terrible applications are out there. You might already know this, but as soon as you turn off a feature that sounds really smart, like disabling flooding, all of a sudden, like a database administrator is like, whoa, whoa, this is how Oracle works. You can't turn that off. So it depends on the implementation and how terrible your life is.
Right, but if you have this enabled, then you have failure domain on all your network, yes?
Yeah, so that would exactly be true, right? Because I am still expanding that, and I would be flooding that, but the difference is that I'm not flooding out all ports. I'm still making unicast replication packets. So it is more, but it's not infinite, right? So I'm still limited by the ingress of the server, whereas in an L2 domain, if I have 10 gig input and 100 gig uplinks, like I'm going to actually not only replicate, but amplify. Yeah. And in this environment, I'm not amplifying. Mm-hmm. So it's bad, but it generally is not catastrophic.
Okay, and in this new solution, you will be informing network which VLANs or tenants are on which compute nodes. So it should help in this situation.
So if you're talking about with the routing-based solution, yeah. So if I'm routing, in that case, only the compute nodes know. And so the compute nodes, if it was flooding, it would be up to the compute node to control that. And the compute node will fall over from replicating traffic well before the network cares.
Okay. Thank you.
All right, Wes?
I have a question for the audience, actually.
Those are my favorite questions. They're gone.
Does anyone want to get hired to operate this kind of stuff? Because I'm running a private cloud, looking to hire people. So we're doing all this stuff in our cloud. Look for the vertical blue stripes. I'm going to be outside.
Wes is doing cool stuff. I can attest to that. So I don't know how we're doing on time. Yeah,
we'll take them offline.
We'll be in the hallway. Come find me in the hallway. Find Dave in the hallway. Thank you very much, everybody.